I'll move on to introduce the last speaker of the session, Professor Ali Abbas, who is a colleague of mine from the University of Sydney. He's a professor in the School of Chemical and Biomedical Engineering, and he's doing some outstanding research and plays an important leadership role in the context of the circular economy. He's a member of the Sydney Nano Institute. We're very proud of Ali. His talk is on the title, Opportunity and Challenges of Nanomaterials in the Circular Economy. Over to you, Ali.
Okay, thank you, Ben, and thanks everyone for attending this talk. This is about the opportunity and challenges for nanomaterials in the circular economy. I am an academic at the School of Chemical and Biomedical Engineering, where I direct the Waste Transformation Research Hub. So, if I can get rid of this one, yeah. The outline of the talk is that I'm going to talk about the grand challenge of circular economy and of waste, and how the circular economy proposition can help to overcome that. I'll talk about the opportunities for nano in the circular, and give some examples from our work in the Research Hub on how we have used the process systems engineering approach to solve some of these projects and problems. And finally, I'll wrap up with the challenges that the nano faces in terms of circular economy. So the waste is a sorrow perspective because it is a wicked problem. It's a problem that every nation around the world faces, including Australia. Here in this slide, I've pulled together some of the data which from around the world, which shows that waste generation is certainly coupled with economic growth. So it's, the more developed countries certainly are producing more waste. In Australia, this is no exception. Our waste is also being generated at an increasing rate, and it's about 6 times the population growth. If we estimate that we are going to improve our recycling processes to deal with the waste generation problem, so therefore we're looking at it as an end-of-pipe solution. In Australia alone, by 2036, we estimate that if we increase the recovery rate, therefore the recycling rate from the current about 60% to, say, 95%, we are going to need some 2,700 facilities to deal with this waste. So this is an enormous industry. There's some lucrative dollars involved here. And however, this is, as I said, an end-of-pipe problem fix. We need to think circular. There are many reasons, because the current patterns of resources use and consumption is not sustainable for the long term, but also there are other problems such as that this is becoming a big impact on the environment, on business. There are also bans by the Australian government to export waste in response also to the China national sword policy of importing waste. Therefore, we need to deal with the waste locally. We need to generate local solutions, local technology. And really, at the end of the day, this has kind of very social aspects in terms of jobs and business. The problem continues to be that we have only about 9% circularity of around, and there's a big circularity gap that is existing. Circular economy is a proposition that's been studied and implemented around the world, especially in Europe. Ellen MacArthur Foundation in the UK is leading this or spearheading the circular economy around the world. And by definition, this is a system that is regenerative by its own nature. It designs out waste and pollution. And on the right here, the diagram, this is the famous circular economy butterfly diagram with the 2 wings, the organic green wing of circulations on the left and the inorganic blue wing on the right here. Circular economy has several steps. The idea is that we will utilize resources most efficiently in the society, in the economy, and reduce the waste. How does it work? There are different ways and different perceptions of how people believe it should work. And, essentially we've got the linear economy where you take resources and you end up consuming them, and at the end of their use, they end up in landfills. The circular economy can be conceptualized as circulations of resources around the economy, not necessarily recycling. In fact, it is not recycling. It should be more around increasing the reuse and the repurposing of materials. Where are nanomaterials in all this? We'll look at this in a moment as we come back. Of course, nanomaterials are in all these materials that we end up innovating and manufacturing and putting on the market and using in society. So our Waste Research Hub is running under this overarching theme, circular economy, with the three verticals: water, wastewater, or carbon and plastics, minerals, and that's in e-waste as well, with a couple of horizontal themes on process intensification, the chemical process engineering core of this, plus also the soft work, modeling, life cycle assessment, circular economy, business model development, and so on. How do we do this, or how do we approach this problem? We are approaching it using a PSE, or Process Systems Engineering Approach, which is really a sub field under chemical engineering, the PSE. And it looks at all these problems from technological, economic, environmental, and social, but addresses them by developing models, design, control, automation, operation, scheduling, and many other activities, including supply chain optimization and so on. So this is our bedrock of engineering that we apply to solve this problem. And of course, we look at it from a big perspective, and not only from a grand challenge perspective, single grand challenges, but we try to address it from the nexus of challenges. So here I just present briefly the energy materials nexus. So we have a lot of energy, renewable energy penetration happening, but that is going to require a lot of materials utilization, a lot of extraction of materials from nature. And in terms of the plastics or polymers, we are also looking at a massive industry. This is heading toward a $6 trillion industry. So these energy and materials end up in all the products that are around us that we use every day. And we are hoping, of course, to go into a 100% renewables future sometime in the distant future. We've been looking at circular economy quite a fair bit, and we've held the first Australian Circular Economy Conference in 2018, and which we learned a big message, which is that circular economy is not recycling. It is, in fact, all about design, and this is the shift that needs to take place, and I hope to pass that message on today from my talk, where recycling is essentially still kind of the linear way of doing things. And we are talking about circular economy, where design is the first and foremost step in the circular economy. This is not to put down recycling, of course not. There's a lot of good recycling stories going around, and we've done a great job in Australia with recycling in the past. The PSC approach is very useful, very helpful, as I will hope to enforce that today. And really, it looks at all the multi-scales, or the different scales of systems, and looking at it from a molecular level up to the unit level, all the way to the system level, where we have a integration of different units. And we use modeling in developing these types of systems, and then we go into the plant design and operation scale. So in this approach, we apply to the entire cycle of these scales. But also on top of these scales, which is illustrated here in a different way in this diagram on the right, we integrate it with the economics, we integrate it with the weather system, we integrate it with the markets as well, such as electricity and carbon markets. And on top of that, we add an optimization layer. We are really certainly not keeping it simple. We can afford to do complex things these days. And we use quite a fair bit of modeling and optimization and CAD drawing software to do all this type of work. This approach is really moving away from the traditional design approach, where you select materials and test them on a system and then iterate back. And this kind of trial and error approach can lead to an enormous level of labor and materials and effort that's going into them, and it's kind of at times sad for me to see a lot of research going on in different materials in this kind of forward way. The way I propose to do it is to combine the process with the molecular design. So in this way, I use all these software along with these methods and algorithms to design materials in process, and we optimize their performance within the process. And that's how I think things should be done. And in this way, we can put on top of our algorithm a circular design objective. And this is really built to avoid the entry of bad products. And by bad, I mean bad chemicals that are essentially going to be nasty for the environment. And in this direction, separately, the other side of the coin here is the policy aspect. And these aspects to limit the use of materials that are going to have low environmental performance. The opportunity for nano, and I'll give a few examples also in a bit from our research, but generally speaking, it is in energy conversion, in energy storage, in water treatment, in waste, construction materials, and also in nano sensors for environmental monitoring. We don't have, of course, time to talk about all these opportunities, but I think this is an interesting area, broadening of how the nanotechnology, nanomaterials can be seen and can apply to the circular economy. From our work, I'll give a few examples from energy and material systems, and I will try to be brief so I can come back to the challenges. With the PSC approach that we are using, we're able to do materials systems engineering. And in this way, we can apply it to heat transfer fluids, we can apply it to thermal storage materials, refrigeration mixtures, carbon capture solvents, and also membrane materials, amongst others like catalysts and so on. So this is for systems, and in this way also, I should say, in terms of some examples, it's also in building systems. So heat transfer fluids applied also in solar heating, solar cooling. We look at these systems broadly from all these, from the broader boundary, and looking at it from all the way from the solar irradiation down to the systems or the different elements of the physics, all the way down to the system itself. And in this example showing on this slide is the solar hot water system driven by the evacuated tube here, which has the mix of the heat transfer fluid. And all these design aspects here, all these design parameters of the system play part and interplay with the actual material, the nanomaterial inside these heat pipes. Again, a lot of algorithms that goes into this. Our way of doing this is reverse engineering these materials within the system. And we develop first up the system model that also goes down to the scale of the nanomaterial, but also the different geometries, embodiments of the design. We reduce the complex model into a reduced order model using dimensionless analysis theory. And we start to learn from this, because at times we find good performance and often we don't know why it works, but slowly and surely we start to correlate that and we start to generate knowledge. For example, here, by scanning through using Monte Carlo simulations, many different chemicals, we are able to start to see a pattern forming with respect to the carbon number of the different refrigerants being used in this, not refrigerant, heat transfer fluids being used in this heat pipe. And we developed this model within the whole entire system, which in this case, the hot water system on top of your house roof. And with the algorithm, we're able to design the heat transfer fluid to achieve the lowest energy loss. We end up with a set of parameters that target the properties of that mix of materials. We end up with several different solutions. This is the objective function, for example, here for the heat loss, and we end up with the topmost or the best performing mixtures coming off here. We're calling them components. We're not naming them because these become commercially valuable mixtures and components. Of course, we simulate that with respect to the daily patterns. So all of this, importantly to say, is that it's not being solved at the nanomaterial, the material mixture level. It's solved at the system level in dynamic mode. Therefore, we capture the performance of that material in the system within the environment it is operating, in this case, the solar irradiation. We extend this to computationally design heat transfer fluids, which have nanofluid components in them for solar cooling, and that is for space cooling. In this case, the design of a new solar-driven adsorption chiller, which has these nanofluids within them, in the same way that we have described previously with these complex models for the heat pipe solar heating system. We further extend this to phase change materials, and phase change materials are very interesting. And again, we can consider a myriad of different nanomaterials that we can spike with the phase change materials, primarily being, in this case, for rooftop applications, wax or, which melt at temperatures around 60 degrees Celsius. And we can extend that. So the big outcome of this is that we can get rid of our solar hot water storage tank, which occupies a lot of space, and replace it with a PCM heat battery. And this heat battery contains these nanomaterials within them to drive the heating of the hot water in the nighttime when the sun is not available. We're developing this heat battery as a key project in our Waste Transformation Research Hub, essentially to recover waste heat. And this is an ongoing active project that we are quite excited about at the moment. And in fact, I should just say that this is also heading towards developing this whole solar roof tile that is going to be agile in the sense that it has this solar storage element to it. Carbon capture materials is another application. And in this application, I should also just mention that the Sydney Nano, which is led by Ben, is tackling these grand challenges. One of them is this one, the CO2 Zero Challenge, looking at ways to use CO2 and capture. And of course, this is a problem that is well known now. It's a grand challenge, and also it is perplexed because of the policy uncertainties around the place. Essentially, we are looking to capture CO2 from different sources, different industries, and look at different ways to convert that CO2 and utilize it in the chemical synthesis and production. One of the examples of how we can use the PSC approach to solve this material systems design is here in this simplified example of the carbon capture process, which requires an extensive amount of heat. This amount of heat can be up to 20% energy loss that can be otherwise sent to the production of electricity. Of course, this technology is now becoming quite exciting in some areas where there is this direct air capture, carbon capture, that is being developed, which is also being led by a company called Carbon Engineering, and they're building the first commercial scale plant in the US, taking the CO2 out of the atmosphere really to drive the CO2 levels in the atmosphere down. So the carbon capture penalty is a big problem. How do we do materials design for this challenge? We can do it via this multi-scale approach that I presented earlier. Otherwise, people have spent enormous research dollars on molecular design or solvent design and have done the optimal solvent design in the lab. But when they take this out to the real system and the real commercial world, it fails, many fail. It's a sad story, as I said earlier. We look at it in a different way. We look at the boundary as a whole, as an entire system, so we can get the optimal techno-enviro-economic objective optimized. And this business is quite a big business. It's a multi-billion-dollar market for these different solvents. So if you can find a nice solvent that can capture the CO2 efficiently, it's quite a good business. So we look at the molecular level using the SAFT equation of state, which addresses the different chemicals using molecular interactions, perturbation theory, and extract out a set of parameters from that equation of state, which we embed in the system model for the carbon capture plant, which is this one here. So the molecular SAFT equation is running together with the entire system model, and we optimize a set of parameters that then allow us to achieve that molecular targeted design for the solvent. Then we go back and test this. Of course, we use an algorithm. We can call this an AI algorithm effectively, but we then test this back in the system to see how much energy reduction we can achieve for the process. And we have found solvent mixtures that can drive the energy kilojoules per kilogram of CO2 captured way down. So that's effectively dollars saved.
Hey, Ali, just a note, we try to wrap up in the next minute or so, just to allow the session to end on time.
I'll do that. Then I will skip then this concrete carbon capture, which is another piece of work that we are looking at, the use of nanomaterials and waste materials in additive advanced manufacturing, applied also in the same spirit to membrane systems engineering with a myriad of other applications. This approach is very broad. The challenge is certainly about the systemic transition to circular economy and how we measure that. There is something I want to point out today, which is called the material circularity indicator. It's an index that one can use to measure the sustainability of a product. And the product can be a plastic bag. As I said earlier, the plastic bag, or mentioned in one of the slides, it is a system in its own right. The material circularity indicator is itself a measure of sustainability, but it contains really two main variables, the longevity and utility. So how long a product survives and how much it's used over time repeatedly. So that is something that is a challenge for all nanomaterials that we need to consider. We've assessed this for a plastic bag and analyzed this, but also there are other challenges, including health and safety, risk, and policy, which should be really discussed on another day. My key message today is that circular economy is a shift, it's a systemic shift from recycle to design. Two, it is the design of nanomaterials and materials in general using a systems approach can be a very effective way to achieve this. And three, integrate circular economy in nano is a big opportunity, but itself requires an entire conference agenda in its own right. Thank you very much, and I point to our second Australian Circular Economy Conference that is coming up. Thank you.
Thanks, Ali. That was a fantastic presentation. I think I'm going to wrap up my role and probably hand over to Sushanta to wrap up this fantastic workshop. So thanks very much, Ali, and a great session. Cheers.
Thank you, Ben.
Thank you, Ben. Thanks, everyone, the colleagues who have joined us, particularly Australia, Japan, which is already Saturday morning for you all, and the colleagues here in Canada, who is already Friday evening. Still, we have quite a sizable audience, and over the last couple of days, I think over 140 attendees have joined across 13 different countries. It's just amazing and successful we are, and happy to listen to all my colleagues' voice and see them after a long time, which itself is amazing, apart from the scientific content of this workshop, and also gave me opportunity to wear my suit, which I don't get these days to do quite often. So it is again a bonus as well. And really the credit goes to the fantastic WIN team, particularly Lisa and Isabella, who has worked tirelessly over the last few months, ensuring that this virtual workshop, which across 4 continents could happen. I really like to thank both of them for their tremendous work working back and forth with the number of researchers, the speakers, the panelists, and so forth. It's just tremendous. Let's have a big round of applause to both Lisa and Isabella for their fantastic work. And stay tuned. We are planning to write kind of a editorial piece about what thoughts and insights that were generated for the last couple of days, and hopefully we'll be able to engage with you all as we move forward with this very critical agenda in terms of sustainability and nanotechnology. Thank you. Have a great rest of the day, weekend, wherever you are.